Maybe I should start. So thanks the organizer for giving me the opportunity to speak here. And just in case I forgot, what follows will be essentially dependent on the roughness theorem of unipotent flows and dependent on the linearization technique developed by Danny Margulis. So in particular, I'm going to talk about will be non-effective. Okay. So, and also, just in case I forgot, I will not talk about applications because I don't have applications right now. But yeah, that's a legal reason. But the motivation to study what I'm going to tell you about comes from counting integral points on certain homogeneous varieties with non-trivial stabilizer. If the stabilizer is trivial, then this doesn't work. But if the stabilizer is non-trivial, then you have a chance, right? So so the plan is I will first draw some pictures and just tell you something holds without any argument. And then I will convert the picture into the language of linear algebra groups. And then I will try to generate the statement to more generality. Okay. So what is the picture? So I first want to look at upper half plane, H, denoted by H, so which is nothing but the set of complex numbers such that the imaginary part of Z is positive. So the upper half plane is equipped with a metric, which let's call it tau, which is just dx squared plus dy squared over y squared. And under this metric, this is constant curvature space, right? So then I have a group action, SO2Z, acting on H. So what's the action? So you take a 2x2 matrix of integral coefficient with determinant 1, act on a complex number. The action is bilinear fractional transformation. Right. It turns out this action is isometry. So because of this isometry, this guy induces the action not only on the tangent bundle, but also on the unit tangent bundle. So this induces SO2Z acting on the unit tangent bundle, right? And I'm looking at the space of the quotient. Which way should I quotient? Right. Right. It's a left action, but I want to quotient right. Right. So now, so this is the space. And now I want to draw divergent geodesic. So let's say this is the upper half plane. So this is C. This is where you have y equal to 0. And so this is 0. And I want to look at this divergent geodesic. So this is a picture on the unit tangent bundle of H. I haven't quotient out yet, but you can project it onto the quotient. So 2C. So what is the picture there? So unit tangent bundle of H, quotient SO2Z, has a nice fundamental domain. Whatever that means, let me draw a picture for you. So T1H mod SO2Z. So looks like this. So this is 0. So this is a fundamental domain, but you have to take into care of the vectors, not just the point. So, all right, so if you project this guy onto here, you would get this. All right. So you get this, makes sense? But I want to convert everything in the fundamental domain, so I'm going to apply some evolution to this part to bring that into the fundamental domain. So then this is the union of this part plus this part. Yes. this is 0. Right. So this yellow part gets mapped to that part. So I have union 2 parts, so this part and that part. So now my dynamics will be something called horizontal flow, right? So this is here. Horizontal flow. Oh, sorry. HS. So this guy acts on the unit tangent bundle of T1H. So let me describe the action for you. So what do I want? So let's take a point here inside T1H. So horizontal flow, I will not define it for you, but the orbit looks like this. So you look at the geodesic passing through this point. So this is x plus, and so this is x minus. So I'm drawing some half circle, which is tangent to this point. And you can draw another circle, which is tangent to x plus. Do I want this? Yeah, let me do the other one, which is tangent to the x minus. And the flow maps this guy to here. Wait, either this way or the other way. Sorry, I forgot. Okay, but the good news about this action is that it descends to action on the quotient. All right. So I want to apply this horizontal flow to this picture. So the divergent geodesic. Right. So let's say what happens in this picture. So instead of take everything, let's just take a segment. Right. So let's say you apply this to this segment. So then for this guy, say this is your x, then the x minus is at infinity. So the circle centered at the infinity will be a straight line here. And the horizontal flow is just translating. So for instance, this line here, after you apply HS, when S is not too large, you will get something like this. I didn't define horizontal flow, but you should trust me, this is what happens. So you have a straight line segment here, all right? Then you should get something like this. All right? Makes sense? When your S gets larger and larger, so you'll get something very right. Then you have to bring this picture back to the fundamental domain. So what you get when S is very large is something like what I'm going to draw. So it's like this. And all the direction is pointing downwards. Okay. So in the limit, it will get equidistributed to some measure on this strip. Right. Okay. Well, whatever that is, you can see the limit measure should be invariant on the unipotent flow, this horizontal flow, sorry. All right, so if you apply this to the other picture, it will become a little bit complicated. So let's take a segment here. So now I'm pointing upwards. So the x minus for, say, this guy will be here. And after you apply horizontal flow to this, you'll be looking at the following picture. So you draw a circle here, and when your S is not too large, you got something like this. So the arrow is pointing that way. And when you got down here, then you got some segment like here. Make sense? So after horizontal flow, something got here get maps to like this. And then you want to bring this back to the fundamental domain, and it's not so easy when you get down more and more close to here, but yes. So, but what happens is that if you look at HS, push forward the measure. So this is a divergent geodesic. So it's equipped with a natural lobic measure on the geodesic. So if you push forward this, let's denote my mu divergent geodesic. And this guy in the weak star topology, well, I want to say that this guy in the weak star topology will converges to the volume measure. So this is, so mu volume is the volume measure on T1H quotient SO2Z. But this is not true, because if you just take weak star limit of this, you will get something that's not locally finite measure, the limit. So what you should do is that there exist AS, some positive numbers, which can be made explicit. So this is at the order of natural log of S. So now the statement is this. So this is the work of Hill and Zhang. Right? Is the statement somewhat clear? So the statement is you look at horocycle flow, apply that to this geodesic flow. After dividing out by some explicit constant, the measure equidistribute to the Haar measure, the measure you want. Make sense? So then I want to translate this statement to the group language of groups. All right, so what do we have? We have X equal to the unit tangent bundle, SO2Z. So remember the fractional transformation acts on H, it also acts on T1H. So not only SO2Z, but also SO2R acts on it. And if you look at this action, it turns out this action is simply transitive. So you can identify, not simply transitive, but with a stabilizer plus minus 1. But with using that identification, you can identify this with SO2R, mod SO2Z. And there's no good reason why I quotient on the right, but I want to quotient on the right. So, and you have something called divergent geodesic. So it's a set equate with some measure. And this set under this identification will gives you T 1 over T, SO2R, what should I say it? SO2Z, quotient SO2Z. So it's a subset of this with T bigger than 0. And the measure here, so what I denoted by divergent geodesic, under this identification becomes up to a scalar, becomes dt over t, which is the Haar measure, the unique T1 over T invariant measure supported on this orbit. Okay. So, and horocycle flow is identified with left multiplication. So I'm quotient on the right. By this matrix. So the statement can be, so equivalently, this statement is just limit s goes to infinity, 1 over as, and 1, 0 s, push forward the Haar measure supported on T gamma mod gamma. So I'm denoting by T equal to this. Is equal to the Haar measure on G mod gamma. So G is SO2R, gamma is SO2Z. Make sense? So now I want to generalize this statement. That means I need to give you what is T, I need to give you what is G, I need to tell you what is gamma, I need to tell you what is this sequence. And this guy, AS, can be made explicit, but today maybe we don't have time to talk about that. Okay, so, all right. So now I want to collect my notation here. So G So this is not that G. This is bold-face G. It's a linear. If you are allergic to this word, I will write examples. Algebraic group over Q. So for instance, GLN, SLN, this guy. So the upper triangular group, and so on. And so now instead of write T, I want to write H. It's a linear, it's a Q subgroup of G. I also want to give you some example. So say here you can take the full diagonal torus inside here. And here you can take the same thing, but with determinant equal to 1. And here you can take the diagonal group here. So I'm writing this in the correct order so that H is contained in the one above. Make sense? Those are examples. So gamma is going to be an arithmetic lattice. So that means gamma is commensurable with GZ. And I want this guy to be contained inside, okay, just one moment. So for instance, here you can take GL and Z. For instance, here you can take SL and Z. For instance, here you can take 1, 1, 0, Z. This is sitting inside there. And this is bold-face letter, and I'm going to use Roman letter to denote the real point. So somehow you can think of linear algebra group as some kind of equations, and one day you decide to solve the equation in R, and that's a set, and it has a structure of Lie groups, and I want to take the connect component of this guy. So for instance, this is GLNR plus, so determinant bigger than equal to 0, bigger than 0, and so here is SONR. And here it is 1, 1, sorry. Here is what? A, B, C with A bigger than 0, B bigger than 0, C arbitrary. Okay. Make sense? And the last, I want to tell you what is this guy. So I have told you what is H, so here is T, what is H, what is G, what is gamma. Now I want to tell you what this is. So G mu G mod gamma is the unique G invariant measure. So I'm assuming this gamma not just commensurable with GZ, but rather contained inside G. Right? So a priori it's not true, but I'm assuming that. The unique G invariant measure, how to spell measure? Supported on G mod gamma. All right. So now you must ask, okay, I can apply this construction to H. So then I know what is mu H gamma mod gamma. But that's the point. You cannot just do that. Okay. So let me. Any questions so far? I want to move on to the second part. Which 1, 2, 3, 4, 5? Uh-huh. No, I don't want gamma to be as gamma commensurable with GZ. So this is not a lattice. Thank you. And this is also not a where? No, this is not a lattice. And this is not a lattice. I don't care. Yeah. But I want to live inside the world of linear algebra groups. That's what I want. So now my goal is to, so that's the first part. The second part is to tell you what's the definition of mu, where is it? Mu H gamma gamma. What time? How much time do I have? 12 minutes. Oh no. Okay, so according to that discussion, you have, did I make the notation mu G? Yeah, mu G mod gamma. So, and because I'm lazy, I don't have enough time, so I will just write mu G. Okay, so part 2 is that, okay, so by that definition, mu H mod H intersection gamma makes sense. So which I denote by mu H is a H invariant measure. So this is measure support on H gamma. Okay, as a set, H mod H intersection gamma can be identified with H gamma mod gamma as a set. So this is map just maps H goes to H. Well, so this is a bijection. However, unfortunately, sometimes this is not a closed embedding of manifold. But I really want this guy to be closed. Otherwise, the measure, if you push for this mu H to the orbit, otherwise it will not be locally finite. That's not what I want. Okay, so the question is the following. When is H gamma or gamma closed? So now I want to give you an argument that will prove H gamma mod gamma is closed, and then I will define a notion called observable. By definition, that will be whenever the argument works. So an argument. So the definition is the following. So suppose we have, not we have, but there is a representation over Q. So over Q just means there's a vector space defined over Q such that SO NQ, BQ, whatever, the Q point of the group preserves the Q point of the vector space. Say G into some GLV. So, and there is a vector V, which is non-zero. Well, you don't have to put, it will follow. Inside the Q point of this vector space, such that this script H, you might want to think of this script H as the C point of H, if you like. It's equal to the stabilizer of this vector in G. Right. Suppose you have such a situation, then gamma, because it's commensurable with GZ, that means gamma will basically, after finite index, preserves the Z structure on V. There's no Z structure, you can choose one, and then it will almost preserve it. In other words, gamma acting on V, you have a sequence of vectors. Each vector will have bounded denominator, okay? So if you have something of bounded denominator, that means it's discrete. In the orbit of G. Okay? So what does that mean? Look at the map from G goes to G mod V. So G goes to G act on V. So this will factor through G mod H. So because actually there's a slight inaccuracy here, but you might assume this map is a bijection without loss of generality. And this is also continuous. So this is discrete and hence closed inside G mod V. And you look at the pre-image of gamma V back to here. So this is closed pre-image. So then you got gamma H mod H, right? So because this is continuous, closed set, the pre-image of a closed set is also closed. So that tells you that this set is closed in G mod H. So gamma H mod H inside G mod H is closed. Make sense? So then by duality and the definition of quotient topology, this is the same as gamma H closed in G. This is the same as H gamma mod gamma. Okay, so I want to quotient on the right, but you know what this is. Can you remind me when there's 5 minutes left? Maybe you should remind me now. 6 minutes. Okay, good. That's good. It's closed in G mod gamma. Okay. Make sense? So when this is true, so definition, H inside G is observable if this is true. So what I write here in the box is true. This is finite dimensional representation, just in case there's any confusion. Finite dimensional representation. Right. So for observable subgroups, this guy is closed. And I can push for the measure on H, mod H intersection gamma to H gamma gamma. Right, so now mu H is well defined. Conversely, Bragg-Rice have shown that if H gamma mod gamma is closed, and if H, G, gamma are arithmetic, defined over Q and something like that, then you can show that H is observable. Okay, so it's equivalent in the end. But we don't have to use that. But it's good to know. 5. Okay, let's say it's 5. So now, part 3. So now I want to give you a sequence. So now I want to assume GH gamma in that case here. Except that now I have to tell you H is an observable subgroup. Q subgroup. If you want to know examples of observable Q subgroups, so there are. So if H is reductive, whatever G is, H is always observable in G. If H is equal to G, then of course G is observable in G. And a counterexample would be any proper parabolic Q subgroup inside any linear algebra group. Those are always counterexamples. They are not observable. Okay. So did I write that? Assume H is observable? Yes, good. Now take a sequence. First, I want to take a sequence gamma n inside gamma by passing to a subsequence. We may assume the following. You can verify we can assume this using the algebra, say, such that there exists. Now I want to describe where it converges to. So I'm trying to describe what's the limit measure. No. So there exists an observable Q subgroup L such that first L should contain gamma n H gamma n inverse for all n. All right. So just gamma n H gamma mod gamma, the translates of H gamma by gamma n. This guy is just equal to gamma n H gamma n inverse mod gamma. Right. So that means however you do, you are trapped inside the orbit of L. Okay. And the second is that L is the smallest one. No proper Q subgroup of L contains gamma n H, gamma n inverse for infinitely many n. Okay, this assumption is too strong. So I just need no proper Q observable subgroup. That contains infinite n. You can guarantee this by passing to a subsequence. And the theorem is the following. Hope you can see the theorem before you go. So in this case, the limit of, so there exists an qualitative, a sequence of numbers, such that the limit of an, I'm very sorry. So there. Okay, that's a theorem. Sorry, that's all I want to say. Okay, maybe I can tell you more, but maybe time is up. So just one moment. In the weak star topology. All right, thank you for your attention. By the way, I guess did I forgot to say thanks to the organizer for allowing me to speak here?
Any questions?
Yeah, sure.
In the example you described before, you did not assume that the gamma n's were contained in the lattice. You were pushing by the horocycle flow, right? So what now is your gamma n used to be your HS.
So you are talking about the example I raised?
The initial example.
The initial example, okay. So,
yeah.
So one, yes, thank you for asking about this.
Exactly.
Okay, so what did you say?
And why do you need it to be in the lattice?
Which one in the lattice?
If you look at the line above, then gamma n is contained in the lattice.
Oh, sorry, thank you for the question. So I basically didn't finish my presentation, but the only reason that I have to assume gamma n is in the lattice is because the following. So you can take arbitrary sequence Gn. Thank you very much. This is a very good question. So arbitrary Gn, you want to study this. So if you made the assumption that the orbit does not diverge, in the sense that there exists K inside G mod gamma compact, if you assume, if this is true, if there exists a compact subset such that this intersection K is not empty for all n. So otherwise, the full orbit will diverge. So the weak star limit will be 0 in the probability, in the locally, in whatever space. And so if this is true, then there exists a bounded sequence inside G, and there exists gamma n such that, so gamma n would be inside gamma, such that delta n, gamma n, h gamma mod gamma would be equal to, what is that? Gn h gamma mod gamma. So the translate of Gn h gamma mod gamma in the case of non-divergence reduces to the translate of gamma n because delta n will be bounded. So it doesn't matter. Make sense? And can I just say one more? So first, so you might be wondering, how do you determine whether it's non-divergence? So I can prove for you that if it divergent, if it diverges, then it's divergent for some obvious reason in the terminology of arc-wise. That is, you can find a representation, find a vector stabilized by h, such that Gn act on that vector goes to 0. And also, I want to ask one question that is motivated by some question asked by Grodnik, Dahl, and Wumo. That is, so even in the case of divergence, let's assume it diverges, doesn't matter. However, there is a nice compactification of the space of G mod gamma, or G mod K mod gamma. So that's what people call locally symmetric space. And there are many compactifications. So for instance, one of them is called Borel-Cell compactification. I want to know, in the divergent case, does the measure converges to some homogeneous measure on the boundary? So the boundary will be some homogeneous space for other group. Okay, so that's the question that I'm not able to answer.
Any more questions?
Could you say something about these constants an?
Yeah, sure. Thank you. Looks like we have talked before. So the constant gamma n will correspond to those h inside h, such that after you translate by Gn or gamma n, that guy will come back to a fixed compact set K. So you fix a compact set K in advance, you look at those h, such that after you apply Gn, that h will goes back to your compact set. Okay? The volume of that is An, quotient out the gamma intersection H. So yeah, I can give you more explicit description later.
If there are no further questions, let's thank the speaker once again.
Thank you.